So in this section, 6.6, we are going to look at elastic collisions or bouncy collisions. And if we remember, we have all different kinds of interactions. We have explosions over here, and we have collisions. And there are two types of collisions, the bouncy type and the sticky type. And what we are looking at today is the bouncy type. So in the bouncy type, there are a couple different situations that could happen. And again, what governs all of this is that the law of conservation momentum, which says the initial momentum equals the final momentum. The momentum at the beginning always equals the momentum at any instant in time for a system. So the first thing that could happen is we could have, let's say at time 0, we could have two particles moving toward each other, like so. And there's different possibilities of what can happen after they collide with each other. One possibility is that they could bounce off each other and head in the direction whence they came. Another possibility is that they both head off in the direction to the right. Or the possibility could be they both head off to the left afterward. So those are the three different possibilities we could have if they're bouncing off each other. Well, let's trace out the algebra here to see the relationships. And so we have P0 equals P. And initially there are two particles, so particle 1 and particle 2. And afterward, they're the same two particles, particle 1, and to denote it afterward, we put a prime. We call it prime, P1 prime, and P2 prime. There are those two particles. And each one of those could then be broken down further so that P1 is M1 V1, P2 is M2 V2, P1 prime is M1. It's the same object, so it has the same mass, but the speed, velocity, would be different. And same thing with particle 2. The mass would be the same, but the velocity of the second one would be different. So we end up with this fundamental relationship for all bouncy types of collisions. So let's look at this specific example of how this might play out. Just moving ahead in our packet. And so we have a bouncy collision. And so we have a bowling ball. So we have our time 0 on the left side of this line and the time afterwards. So this is how we can keep track of do our accounting. So we have a bowling ball rolling eastward. So east is positive, west is negative. So we've got a bowling ball rolling eastward. It is 7.0 kilograms. And we have at 4 meters per second. And so that's a positive direction. So it's plus 4 meters per second. And there's a different bowling ball headed westward at 6 meters per second. So that means its velocity, its speed is 6 meters per second, but its velocity is negative because it's headed for the negative direction. And so we have 4.0. And we are told that after the collision, the 4 kilogram ball heads eastward at 2 meters per second. So afterward, we've got V equals positive 2 meters per second, and it's 4 kilograms. To draw before and after diagrams and determine the velocity of the 7 kilogram ball. So we've got the 7 kilogram ball, and you remember that there are a number of different possibilities in this case about what could happen. So our accounting of the momentum will allow us to figure out what happens. So P0 consists of P1 plus P2. And the momentum afterward, P, is P1 prime plus P2 prime. P1 is M1 V1. Momentum 2 is M2 V2. And afterward is M1 V1 prime and afterward is m2 v2 prime. So what we are looking for is the velocity of this. v1 prime is what we're looking for. So we can solve for that. And the way we solve for that is we're going to subtract m2 v2 prime from both sides. So we have m1 v1 plus m2 v2 minus m2 v2 prime, which is m1 v1 prime. And to get v1 prime, we will divide both sides by m1. So we are left with this whole thing divided by m1. So now we can plug in the numbers to find out our solution here. So mass 1 is 7. The velocity was 4. M2 had a mass of 4 and had a velocity of minus 6. And M2 a velocity of 4, and its velocity afterward is plus 2. All of that divided by 7. So v1 prime is, we've got 28 minus 24, and 8 on this side. So 36 minus 24 is 12. 12/7. We did a little bit of a mistake there. It's the 8 is negative. So we've got minus 32 plus 28 is plus 4. So that gives us 4/7. 4/7 meters per second. Excuse me, negative 4/7 meters per second, because negative 32 or 4. So negative 4/7. So it's moving like this, minus 4/7 meters per second. Now we could do a check on this to see, does the momentum before equal the momentum afterward? Well, the momentum before is plus 28 and minus 24 gives us a plus 4. So then we can ask ourselves, does this situation give us a plus 4 momentum afterward? Well, afterward we have m1, which is 7, and v1 prime, which is minus 4/7. And the particle 2 has a momentum, a mass of 4, and a velocity of 2. So plus 4 minus 4 plus 8. So we're left with plus 4 on this side and plus 4 on this side, and that checks out. Now we could have listed our terms here beforehand. That makes it a little bit easier. We mostly pulled those numbers. But the interesting thing is the momentum before is plus 4, and so the momentum afterward must be plus 4. And we saw this in a multiple choice question we did earlier today as well. We look at the momentum, initial momentum, and the final momentum to determine if it's conserved. So that concludes our examination of a bouncy collision. In the next installment, we are going to look at a sticky collision, and we'll see you then.